Good evening, everybody. My voice is clear now. Hello?
Yes, you can start. We can hear you.
Okay.
Yeah,
Okay.
no
Thank
problem.
you. Thank you.
Mhm.
This presentation is about photoreduction of hexavalent chromium by zinc sulfide zinc oxide supported on MCM-41 based on blast furnace slag and electric arc furnace dust. Authors are Enas Amdeha, researcher of applied physical chemistry, Egyptian Petroleum Research Institute, Rasha S. Mohammed, Assistant Professor of Physical Chemistry, Egyptian Petroleum Research Institute, and Abdelghaffar S. Dohmis, Assistant Professor of Environmental Chemistry, Egyptian Petroleum Research Institute. Environmental pollution in the 21st century is marked as one of the most significant issues. Although water is the origin of life, there are million people around the world suffer from the shortage of healthy and clean drinking water, as it has been contaminated by numerous organic and inorganic contaminants existing in the manufacturing waste, resulting in about 75% of all disease in developing countries, especially for females and kids. On the other hand, over 2 billion tons of solid waste are produced annually and represent the major source for environmental pollution, with an increase in number over the next few decades. According to the Sustainable Development Goals, material science research has to focus on recovering methods and proper waste managing. This includes two major issues: wastewater treatment and solid waste through one process. In other words, you can say that it means removing waste by waste as a step towards environmental protection. Water pollution comes from various sources. Hazardous pollutants in wastewater include biological pollutants like bacteria, virus, parasite, and algae, while chemical pollutants are divided into two major parts: organic pollutants and inorganic pollutants. Organic pollutants like phenols, dye, and pharmaceutical compounds, and inorganic pollutants, for example, heavy metals, arsenic, iron, and nitrate. These pollutants cause a decrease in water quality. Heavy metal pollution sources are extensive, containing paint manufacturing, metal finishing, electroplating, laser tanning, electrical industries, fertilizer, pigment industries, and wood manufacturing. As one of the common heavy metal ions, hexavalent chromium has been identified as a highly toxic and fluoride carcinogen and mutagen, which influence the environment and the human health. In contrast to hexavalent chromium, characteristics of trivalent chromium are relatively stable. Moreover, trivalent chromium is a micronutrient of critical value for the human body. Therefore, reducing hexavalent chromium into trivalent chromium is an urgent task to remediate the pollution of hexavalent chromium in the environment. A variety of methods have been widely studied to achieve successful hexavalent chromium removal, such as absorption, biological methods, membrane filtration. However, the wide use of such technologies is limited by common disadvantages, such as high cost, low performance, and secondary pollution production. In comparison, photocatalytic reduction with metal-free, non-toxic, and chemical stability are considered one of the most encouraging environmental remediation approaches in the future. Zinc oxide is one of the most photocatalysts to reduce hexavalent chromium because of its eco-friendly chemical stability and low cost. Under UV light irradiation, zinc oxide can be photostimulated, and the electrons in the valence band are excited to the conduction band, leaving behind positive holes. These electrons take part in the hexavalent chromium reduction. In the introduction section, we talked about solid waste. One of the solid wastes are produced by steel production. Steel production, there are two methods for steel production. The first one is recycling scrap in electric arc furnace. This furnace produces waste, which is electric arc furnace dust. This dust consisting mainly of iron oxide and non-ferrous metals like zinc oxide, lead oxide, and calcium oxide. World crude steel production up to 1,800 million tons in 2018. Each ton of steel produces about 15 to 20 kilograms of electric arc furnace dust. The global produced electric arc furnace dust volume varying from 6 to 8 million tons worldwide. As zinc is regarded as the most significant component of electric arc furnace, the special recovery of highly efficient zinc from electric arc furnace dust is an attractive option due to its low production cost. The second waste is the blast furnace slag, which is produced from blast furnace for reduction of iron ore. This slag is a complex mixture of high temperature alkali earth silica with chemical structure of silica, alumina, and calcium oxide. Blast furnace slag is an economic potential raw material for silica processing, since blast furnace slag have high amount of silica over other slags. Especially MCM over the 2 decades, over the last 2 decades, ordered mesoporous silica have been formed with excellent mesoporous structure, having high surface area, which is more than 1,000 square meters per gram, tunable pores in the range between 20 to 100 angstrom, and wide pores more than 0.6 cubic centimeter per gram. And it possesses high thermal stability up to 800 degrees. These excellent properties give silica-based photocatalysts great attention for water treatment purposes due to high surface area, which enhances the absorption performance and hence the low photocatalytic performance. So, aim of this work is to prepare mesoporous silica MCM-41 from blast furnace slag, and we will prepare zinc oxide and zinc sulfide from electric arc furnace dust as an environmental and economic method. Also, to prepare zinc sulfide, zinc oxide supported on MCM-41 to be used as a photocatalyst for hexavalent chromium photoreduction under UV irradiation. For experimental section, MCM is prepared from blast furnace slag, zinc oxide is prepared from electric arc furnace dust, and zinc sulfide is prepared from previously prepared zinc oxide by hydrothermal method, and zinc oxide supported on MCM. Also, zinc sulfide, zinc oxide will support on MCM by ultrasonic synthesis method. The second part is evaluation of these prepared photocatalysts for hexavalent chromium photoreduction under UV irradiation. This is a diagram explaining the preparation method. And this is the photocatalytic apparatus in which a UV lamp in quartz jacket is immersed in a glass reactor containing the polyethylene solution. The polyethylene solution was stirred using a magnetic stirrer and supplied by oxygen by air pump to ensure solution homogeneity. The used UV lamp was 254 nanometer wavelength, was used as an irradiation source. Prior to irradiation, the polyethylene solution over the catalyst was kept indoors for 1 hour to attain absorption equilibrium. Results in discussion. The first is the characterization of the prepared photocatalyst. We will discuss it from XRD, TIM, FTIR, surface area, and photoluminescence. The first is the XRD. For MCM, the left figure for MCM, an amorphous peak at 2 theta equals 23 was observed, which is a characteristic peak for MCM, while the right figure shows the small angle X-ray diffraction pattern of MCM-41. The separation is confirmed by the presence of a strong peak at 2.69 and 2 weak peaks at 2 theta equals 4.5 and 5.4. These planes, 100, 110, and 200, suggesting a hexagonal mesostructural substance with high degree of ordered structure. For zinc oxide sample, the characteristic peaks for zinc oxide is appeared at 2 theta equal 31.9, 34.6, 36.7. All characteristic peaks are assigned by stroke. For zinc oxide MCM, the peaks of zinc oxide have a small shift to slightly lower angle with very low intensity. For zinc sulfide, zinc oxide MCM, the peaks attributed to zinc sulfide is appeared. The low intensity peak of zinc oxide in zinc oxide MCM and zinc sulfide in zinc oxide MCM are attributed to the low concentration and good diffusion. This figure is the nitrogen absorption solution isotherm of the prepared samples. According to the IUPAC classification, MCM-41 exhibits type 4 isotherm with each one hysteresis loop at relative pressures more than 0.3, indicating the presence of a well-defined series of standard mesopore channels, which is important for efficient absorption. Zinc oxide exhibits type 4 isotherm with H3 hysteresis loop for zinc oxide microsphere. For composites, whether it's zinc oxide MCM or zinc sulfide zinc oxide MCM, the isotherms are of the same type of MCM-41, concluding that there is no structural collapse induced. The surface area of MCM-41 is about 937 square meter per gram, and the pore volume is about 0.847 cubic centimeter per gram, and the pore diameter is 2.77 nanometers. For zinc oxide, the surface area is only 51.7 square meter per gram. The surface area of the composite is slightly decreased. This slight reduction in surface area is due to the incorporation of zinc oxide and zinc sulfide. The suggested incorporation is also confirmed by the increased pore volume up to 3.2 nanometers. As FTIR is an important technique for a recognition of functional groups, we study it. This slide, we found that for MCM-41, there is a silanol group at 3,500, and this is a water group, and this is a silicon-oxygen-silicon group. For zinc oxide sample, the peak at 3,449 corresponds to OH stretching vibration of water molecule in zinc oxide, while the zinc oxygen bond is in the range 700 to 400. The composite sample exhibits similar vibration bands of MCM-41 with no special differences were observed due to the overlapping with MCM-41 band, and also as a result of the incorporation of zinc oxide and zinc sulfide nanoparticles into MCM-41. This is the TEM images or transmission electron microscope images of the prepared samples. For MCM, this image confirmed the preparation of MCM from blast furnace slag, which is showing a hexagonal distribution with mesoporous structure. And the uniform pore size was about 2.7 nanometers. For zinc oxide sample, the particles of pure nano zinc oxide exhibited a small nano-sized grain of spherical particle of size about 25 nanometer diameter, and there are some agglomeration. For composite samples, after incorporation of zinc oxide and zinc sulfide, the mesoporosity of MCM-41 does not disturb, and zinc oxide and zinc sulfide particles can be distributed more equally around MCM. Also, there is a little zinc sulfide and zinc oxide particles on the outer surface of MCM, and they are lightly aggregated. This is the TEM and EDIS, or energy dispersive X-ray spectroscopy for the composite sample, zinc sulfide, zinc oxide, MCM, exhibiting the elemental mapping of oxygen, silicon, zinc, and sulfur. The inclusion of these elements supports the composition of this composite, indicating homogeneous distribution of zinc oxide and zinc sulfide on MCM-41, confirming the heterogeneity. Photoluminescence. As we know that the principle of photocatalysis depends on the enhanced separation of electron and hole, as they play the main part in the process. The fast electron-hole recombination is a big photocatalytic challenge. To inhibit the electron-hole recombination, composites are prepared and used to enhance the efficiency of photocatalysis. The PO intensity is directly related to the recombination rate of photo-induced charge carrier. Therefore, under light irradiation, the higher PO intensity indicates the higher recombination rate of electrons in the holes. This is the PL spectra of the prepared sample. This sample exhibits two peaks compared to zinc oxide MCM sample. The zinc sulfide, zinc oxide MCM, the peak of this composite is dimension, indicating that the recombination of photogenerated electron holes is restricted in zinc sulfide, zinc oxide MCM composite due to strong electron migration from zinc sulfide to zinc oxide. Following photocatalytic activity principles, the improvement of photocatalytic activity for this composite sample, which is zinc sulfide, zinc oxide MCM, can be concluded mainly by high efficiency of transfer of the charge. The second part is hexavalent chromium reduction. To understand the importance of supporting on MCM and the mixing with zinc sulfide, the photocatalytic performance of these photocatalysts were evaluated by photocatalytic reduction of hexavalent chromium to trivalent chromium under UV irradiation. We will study the effect of different catalysts, effect of chromium concentration, effect of dose, pH, and recycling. For zinc oxide exhibited almost 40% of hexavalent chromium reduction, while when supporting zinc oxide on MCM, the activity is enhanced up to 58%. While when adding zinc sulfide, the activity is increased up to 94%. The right figure, in this figure, there are two more control experiments to confirm our results, which are, the first one is photolysis under UV only without catalyst, and the removal was only 4%, confirming the stability of hexavalent chromium under light. The second experiment is is making the same experiment without light, in dark only. We found that the efficiency was about 49. When the light is on, the efficiency is increased up to 90-fold due to the synergetic effect between absorption and photocatalysis. The rate of photocatalytic activity of zinc oxide supported on MCM is enhanced over zinc oxide only, and the rate is enhanced up to 0.0067 for zinc sulfide zinc oxide MCM. This enhanced behavior can be regarded as the reduced rate of electron hole pair recombination. To study the effect of photocatalyst dose, the initial chromium concentration was 20 ppm at pH equal 2.1. As we can see, the photocatalytic rate was enhanced and decreased and increased from 0.2 to 0.0045 up to 0.0155 -1 by increasing the photocatalyst amount. This is due to the increase in number of surface active sites and more photocarriers with higher surface area that support more contact between the reactant and the catalyst. Considering the economical point of view, 0.5 gram will be used for another experiment. To study the effect of chromium concentration, 0.5 gram of catalyst was used, and the initial chromium concentration was ranged from 10 to 50 ppm. By increasing chromium concentration, the rate of reaction is decreased, as the radicals are insufficient to react with hexavalent chromium due to the fact that the photocatalyst could give only a definite number of active sites, and the catalyst would be disabled with high concentration. To study the effect of solution, pH 0.5 gram of catalyst was used with initial chromium concentration equal to 20 ppm, and the pH ranged between 2.1 to 11.1. By increasing the solution pH up to 11.1, the hexavalent chromium removal rate is decreased. At higher pH value, the surface has become more negative, that are resistant to the absorption of negative chromate ions. Additionally, at higher pH, the deposition of occupancy of chromium hydroxide on the photocatalyst surface reduces the contact area of the catalyst with the reactant, which decreases the photocatalytic efficiency. This serves as a barrier to photocatalytic electron for chromate ions that led to a photocatalytic decline. Therefore, hexavalent chromium reduction reaction was favorable by zinc sulfide zinc oxide MCM under acidic conditions, as the catalyst surface is positively charged, which enhances the absorption of negatively chromate ions and in turn enhances the whole photocatalytic process. To examine the photostability of zinc sulfide zinc oxide MCM, recycling photoreduction studies have been performed, in which the photocatalyst was collected by filtration after each cycle and washed 5 times with 1 molar nitric acid and deionized water. After that, it dried for 12 hours at 100 degrees. This slide exhibited that the photocatalytic activity can be sustained during the entire reaction phase, and after 4 cycles, there is a minor significant loss of activity. A comparative study of the prepared zinc sulfide zinc oxide MCM composite with previously reported work on the photocatalytic activity was carried out. From this study, The prepared zinc sulfide zinc oxide MCM composite exhibited outstanding high photocatalytic activity, and it would be a promising photocatalyst for hexavalent chromium reduction in wastewater, with efficiency up to 94% after 3 hours, with only 0.5 gram per liter as a dose. Conclusion: a simple way was developed to synthesize zinc sulfide zinc oxide MCM photocatalyst derived from electric arc furnace dust and blast furnace slag. The characterization, including XRD, TIM, FTIR, nitrogen absorption dissolution isotherm, and photoluminescence, demonstrated the formation of MCM-41 and zinc oxide from waste with high purity and proved a high surface area, either for MCM-41 or the composite. On the other hand, TIM and EDX mapping demonstrated the good nano zinc sulfide zinc oxide supported on MCM-41 and the uniform distribution. Although the photoreduction activity of zinc sulfide zinc oxide MCM nano composite has obvious efficiency compared to zinc oxide alone and zinc oxide MCM, achieving about 94% photoreduction of hexavalent chromium after 3 hours under UV irradiation. The slight activity loss after 4 cycles, while the efficiency is still up to 84.7%, reveals the good stability and the photoreduction properties of the prepared catalyst. Based on these results, zinc sulfide zinc oxide MCM composite material seems to be high efficiency, green, stable, environmental and economical alternative to be used as a photocatalyst for the photoreduction of hexavalent chromium. Thank you. Any question or any details are required, then contact me via email. Thank you.